Hello, everybody. Thanks, Asta, for accepting our invitation to talk here today. Asta is a postdoc at the Niels Bohr Institute in Copenhagen. She got her PhD at the University of Canterbury in New Zealand, and then she joined the ENS in Lyon as a postdoc. Asta's research topic is general relativity cosmology and investigating consequences of the inhomogeneous distribution of matter in our universe from various perspectives. In particular, she's focused on anisotropic imprints in observables and their geometrical interpretation, cosmography, dark energy signatures in observables in non-trivial geometries. Today, she will present the dimming of light in general relativity on the possible emergence of apparent dark energy effects. Asta, you can start, please, when you're ready.
Thank you. Thank you very much for this introduction. As Eleonora was mentioning, I'm going to talk about dimming of light in general relativistic cosmologies, and I'm going to do that in a fairly general setting, so not assuming anything about the space-time geometry. In particular, I'm not going to assume anything about local metric symmetries, and then I'm going to discuss in this setting the possibility of obtaining an emergent or an apparent dark energy effect without necessarily violating the strong energy condition. So first I will give a summary of the evidence that we have for dark energy in modern cosmology, and I will then review some important results that we have within the FLRW class of geometries for distances and redshifts when the strong energy condition is satisfied. In this case, the distances are bounded in a certain way as a function of redshift, with a bound that we can call the Milne bound, and which I'm going to talk about in some more detail. And I'm then going to talk about distances and redshifts for general geometries where we do not assume the symmetries of the FLRW metric. And I'm then going to formulate a necessary requirements for obtaining super Milne distances, so distances that violate this Milne bound that we otherwise have in the FLRW class of geometries. And I'm going to discuss how we can obtain such super Milne distances without actually introducing a dark energy component or another component that violates the strong energy condition. So dark energy, or the cosmological constant, was first introduced by Einstein in his first paper applying general relativity to cosmological scales, and there it was used to keep the space-time that he was considering static, and that is quite opposite, you could say, to what the cosmological constant is used for in modern cosmological modeling. Here we are using it to make the expansion of space go faster, and this need for an accelerated expansion was first seen with observations of supernova light curves in the late 90s, early 2000s, where what one could see that in order to fit the range of supernova, and in particular the higher redshift supernova of the sample, one needed a cosmological constant on top of the contribution from ordinary matter in order to make the distances larger towards the higher redshift. So you can see here the top curve here is representing the model that includes a cosmological constant, and it fits better by eye than the curves that just contain ordinary, than the FLW curves that just have ordinary matter. And today we have better supernova statistics, both in terms of redshift range and angular coverage. And so the statistics for this result has gone up, and the best fit has remained quite robust. So this is one of the strongest independent constraints that we have on dark energy. We have there's other complementary probes of dark energy. There's the cosmic microwave background at the larger scales, where the angular position of the first peak in the temperature power spectrum can be used to constrain the dark energy component as well. There are baryon acoustic oscillations, which probe the size of the sound horizon scale in the present epoch matter distribution, and this we typically estimate through galaxy or quasar two-point correlation functions. There's also the cosmic microwave background at small angular scales, where we have lensing observations and the integrated Sachs-Wolf effect, where the background cosmology is also entering and becomes important for these effects. There are cosmic chronometers, where we can exploit that if we have galaxies where we know relatively well their relative ages, we can get a direct measurement of the universe expansion rate from this. There are also interesting upcoming measurements of redshift drift, which are measurements of temporal changes in the cosmological redshifts that we observe from individual galaxies. And so if we are to explain dark energy from some alternative mechanism than a cosmological constant, we in principle, we need to account for all of these observations, and in many of these observations, well, at least the primary ones that we have for supernova and the cosmic microwave background at large angular scales, we are probing dark energy directly through the cosmic distances that we infer with our measurements. So it's important to understand exactly how dark energy enters in these distance definitions that we have in cosmology. So two of the most widely used distance measures in cosmology are luminosity distance and angular diameter distance. Luminosity distance is defined by the square root of the ratio of the intrinsic bolometric luminosity and the flux observed from an astrophysical source. And so intuitively, the greater the luminosity distance, the greater the dimming of light on the path from the source to the observer. And then we have the angular diameter distance. It is defined by the square root of the area of the emitting source divided by its angular size in the observer's telescope. And intuitively, the greater the angular diameter distance, the greater the focusing on the photons when they pass from the emitting source to the observer. And whenever we are in a Lorentzian spacetime where photons are conserved along the bundle, we can apply Etherington's reciprocity theorem that nicely relates luminosity distance and angular diameter distance through a factor of 1 plus redshift squared. So when we're in this setting, we can use these distances interchangeably, and I'm going to do this in this talk, having this relation in mind. Okay. So before we move on to considering general geometries, it's useful to review some well-known results that we have in the FLRW class of geometries. Here we have some important results on that bound distances when the strong energy condition is satisfied. So basically we have that a given FLRW model that is subject to the strong energy condition is bounded by the Milne universe model in this way. So here we have on the right hand side we have the dimensionless angular diameter distance in the Milne universe model, so the empty FLRW model, whatever energy momentum tensor we then have with ordinary matter or radiation is going to decrease our dimensionless angular diameter distance. And similarly for the luminosity distance, we can write down a similar relation. And intuitively, this is because ordinary matter and radiation are acting gravitationally, so they act to decrease distances between objects, and so any addition of ordinary matter or radiation will only decrease distances relative to the empty Milne universe. So we can say that spacetimes that violate these bounds have super Milne dimming of light, and I'm going to use this terminology in this talk. So what can we expect when we go to more general geometries that do not obey the FLRW symmetries? Here matter and radiation are still going to act to decrease distances in the space-time, but photons will now be going through structures, and they will carry information about these in some projected sense. And it's then the claim that sometimes photon propagation through structures can be systematic, such that there can be a sort of an accumulated dark energy effect that gives rise to an observed dark energy in the observer's telescope when he is interpreting things within the FLRW class of models. And a simple example So we know that this can happen already. A simple example is an observer that is placed in the center of a void region modeled by a Lemaitre-Robertson-Walker model. Here, when photons propagate towards the observer, they are propagating from the outskirts of the void, where densities are relatively high, so the expansion rate is relatively low, towards the center, where the opposite is the case, so the density is relatively low, and so the expansion rate is relatively high, and this systematic propagation towards fast expanding regions is leading to distances that can mimic dark energy in the observer's telescope, and this is known since the late 90s or early 2000s. And you can say that the Lemaitre-Robertson-Walker models have other problems when applied to cosmology. They are violating the Copernican principle, and so you could argue that they are not really reasonable for modeling the universe at the largest scales. But we can think that since it's possible to obtain such effects in a simple toy model, it may be possible to obtain apparent dark energy in more complicated spacetime. So it's worth assessing in detail the conditions under which we can obtain such emergent dark energy effects. So I've done this in this paper, and we need to make some basic starting assumptions. So here I assume a Lorentzian spacetime with the usual Levi-Civita connection that we also have in general relativity, and I'm going to assume that light is described in the geometrical optics limit, so light can be considered test particles in our spacetime. And we are also going to assume a congruence description for the emitters and the observer of light in our spacetime. And what this essentially means is that we have a continuity description. So we are neglecting issues of, for instance, if two sources are crossing or merging. So there are singularities appearing in by the crossing of world lines. This may be a bit more complicated to incorporate, but as long as we are in a regime where we can neglect such effects, this description should be suitable. And then we can also introduce some useful parameters. So we introduce lambda as the affine parameter along the individual light rays ending up at the observer, and we define we can define E as the photon energy function, and as measured by the observers and emitters along the photon bundle. It's also useful to introduce what I call effective cosmological parameters. So parameters that, in a sense, replace the FLW Hubble parameter and deceleration parameter in a certain sense when we generalize the geometry. So the way I do this here is to introduce this effective Hubble parameter, which is given by the derivative of the inverse photon energy along the photon null ray. So this is so there's a sense in which the photon energy here, the inverse photon energy, plays the role of a generalized scale factor, if you will, along the observer's past null cone. And this effective Hubble parameter reduces to the FLW Hubble parameter in the FLW limit. But yeah, it's well defined in this general geometrical setting that we are considering. And in a similar way, we can introduce the effective deceleration parameter, which is essentially given by the second derivative of the inverse photon energy. And these generalized Hubble and deceleration parameters are natural in various settings where we consider cosmological, the geometrical formulation of cosmological distances from a general perspective. So they also show up in approaches to cosmography, which I have described in this paper and some follow-up papers. Okay, so now we can use these variables that we just introduced in order to write down the geometrical prediction for redshift in this general setting that I just described to you. So a useful function of the redshift that we can consider is this one. If you remember back from one of the previous slides, this was the dimensionless angular diameter distance in the Milne universe model. So that's a good reference to have on the left hand side, and then on the right hand side we have what this function of redshift is given by in terms of the effective cosmological parameters that we just introduced, and the affine distance to the emitting source. And now you see why it was exactly useful to introduce exactly these generalized cosmological parameters. It is because they appear in a natural way in the distance redshift law, you could say. And you see that here the effective dimensionful deceleration parameter is entering with a double bracket, so a double average that looks like this. Okay, so in order to get a bit of intuition about this expression, we can look at how the effective cosmological parameters look, which kind of kinematical variables enter in these compact writings of effective Hubble and deceleration parameter. So it's useful to write down the effective Hubble parameter in a multiple decomposition, where we can expand in the direction of the incoming light E. So this is really the direction in which the observer sees the source in the telescope. And so when we do this, we have that the monopole term theta describes the volume expansion, the isotropized volume expansion rate of the observer and emitter congruence. So this is a very natural extension of the FLW Hubble parameter, because this is what the Hubble parameter is telling us about in FLW physics, how space is isotropically expanding around the observer. But now we also have anisotropic contributions here, and we see that we have a dipolar term whenever the observer is not geodesic. So whenever we apply a force to the observer, there's an important quadrupolar term here that comes from the shear tensor describing the anisotropic deformation of space. So that incorporates the effect that space is now going to expand anisotropically around the observer. So when the observer is looking along a direction where space is expanding more than the average direction on his sky, we expect this observer to see an enhanced value of the Hubble parameter in this direction. This kind of multiple decomposition was first considered by Ellis and his collaborators in the 80s, and I'm then using similar decompositions here for the purpose of this work. You can, in a similar way, consider the effective deceleration parameter and its decomposition into multiples. Here you can expand in a similar way. So the expression is a bit more complicated. It goes to higher order. But the principle is the same, and you can see that many of the same parameters enter here as I just introduced. So theta, the volume expansion rate, the forward acceleration of the observer congruence, and the shear tensor sigma. And we have gradients of these, so both spatial gradients and the time derivatives of these variables. We also have omega entering here, which is the vorticity tensor describing rotational degrees of freedom of the observer and the emitter congruence. And we can look at which of these terms survive in the FLW limit. It's only this single term that survives in the co-moving FLW limit, although the terms arise due to inhomogeneities and anisotropies in the space-time. And it's also this term which it can in general be interpreted as the local isotropized acceleration of length scales between test particles in the space-time. So this is really how we usually think of the deceleration parameter. This is the interpretation of the deceleration parameter in FLW physics, but because we have this hierarchy of correction terms here, we lose this simple interpretation of the effective deceleration parameter. So you're really only to think of the effective deceleration parameter as a useful effective parameter that enters the expressions for the observables on a similar footing as the FLW deceleration parameter, but it does not inherit all of the nice simple interpretations that we have in FLW physics. And that's very important to keep in mind when we want to analyze data in a more model-independent fashion. Okay, so we can now look at having a bit more intuition about these effective cosmological parameters that feed into our expression for redshift and distances in our general geometry. We can look at what happens when we start imposing energy conditions. So we are now going to assume that we are in general relativity, and we are going to impose the null energy condition. Then we immediately have through Sachs optical equations that we have this bound on angular diameter distance in terms of the affine distance to the source. Then we have, from the expression on the previous slide, that we can substitute to get the following upper bound on the dimensionless angular diameter distance in our general spacetime. And you can now perhaps see that we are not too far in being able to define something similar to the Milne bounds that we had in the FLW scenario. That is, if we are able to bound this parenthesis to be larger than 1. So we need this double bracket of the effective deceleration parameter to be larger than 0. So, and the question is then, is that possible to obtain by applying energy conditions? And the answer is that that's not possible, exactly because of the reasons that I just sketched to you, that the effective deceleration parameter is quite complicated, and if we are imposing the strong energy condition, all that's going to be useful for is to bound this term in the monopolar contribution to the effective deceleration parameter. So all other terms are in principle left unconstrained, and so it's generally not possible to bound the deceleration parameter by imposing the strong energy condition. Yes, so it's possible to have negative values of the double integral of the effective deceleration parameter while satisfying the strong energy condition, and so it's possible to violate the Milne bound in such spacetimes. And we have a simple example where this happens, namely the Lemaitre-Robertson-Walker models that I discussed previously. And now we can see what happens mathematically in these models is that these terms that involves the spatial gradients of kinematic variables here are going to contribute systematically along the null rays. So because the photons are propagating from regions of smaller expansion rate to larger expansion rate, there are systematic non-cancelling contributions from these terms. And these are then degenerate in the observer's measurements. They are degenerate with contributions that comes from the time derivative of theta. So that is what gives this apparent dark energy effect. Some conclusions. These results that I presented, they present a way to classify spacetimes that could have apparent dark energy signatures in the distance redshift graph. So there's a particular geometrical integral constraint that must be violated in order to produce such an apparent dark energy effect or excess dimming of light. And it's this condition basically that we need to violate systematically in order to measure super Milne distances to the stars and galaxies in our telescopes. And I've discussed why it is possible to violate this geometrical constraint without necessarily violating the strong energy condition. And this is contrary to our intuition that we have from FLRW physics. So some interesting questions that arise from this kind of analysis is whether it's possible to obtain these kind of apparent dark energy effects that we observe in Lemaitre-Robertson-Walker models in more realistic spacetimes. So spacetimes that have some notion of statistical homogeneity and isotropy, so that they respect the Copernican principle in some reasonable interpretation. Yes, we could think of, for instance, considering simple model spacetimes such as Swiss-cheese models. We could also think of looking into cosmological simulations and look at what kind of if we can find any constraints in these simulations that prevent super Milne dimming of light, and whether we could break such symmetries or constraints. Yes, these I think are interesting questions to look at. So thank you.
Thank you so much. Thank you for the nice talk.